This is Joel, and in this video we'll talk about Route Reflector. Now the prerequisite for this is that you would need to have some knowledge on BGP. So you can actually go down to my channel and look at the routing playlist, where you will find dedicated videos on both basic and advanced topics of BGP. Cool. That being said, let's get into it. Route Reflector, right? Let's start with the why. Let me grab my pen here. Okay, so why do we need this, right? Why do we need this design? Now you need to look on the left hand side. We have a typical iBGP setup, right? We know iBGP is nothing but BGP peering, where the peers are within the same AS, correct? Now you have a simple iBGP setup here. Let's remember there's a golden rule in iBGP. What is that golden rule? When a peer learns the routes from another iBGP peer, this guy is not allowed to forward or re-advertise those routes to any other peers, right? That rule is basically called split horizon rule. And because of this rule, the only way to get around this rule is that you would need to have full mesh between. So you need to have like this, right? The full mesh between every other iBGP peers in the network. And because of that, the number of iBGP sessions between the peers will drastically increase. Like in this case, you will end up, because you have 7 iBGP peers, you will end up having around 21 iBGP sessions, which is, and that number is obviously going to increase as you have more and more as the network increases or network becomes larger, right? So on the right hand side, we have the same, same network, but with the route reflector added, right? The idea here is that the basic funda here is that, you add a device like a route reflector, or in fact you can repurpose one of the devices as a route reflector as well. In this case, we have added an extra device called route reflector, right? It's just another BGP device, right? Nothing very fancy. It's your regular router, which is going to have the route reflector functionality. And once you add this device, you basically make few devices as the clients for this route reflector, as you see here, right? These are the 4 clients. And because these are the clients, what they can do now is they can send the BGP updates all the way to route reflector, and the route reflector will reflect it back, right, to all the other clients in this way, right? Because of this, what has happened? We have solved the problem of too many iBGP sessions. We don't need we don't need the full mesh anymore, because a route reflector relaxes this split horizon rule, right? For route reflector, doesn't have the split horizon rule, which means that it can receive the routes from clients and then it can reflect it back, which was not allowed in your normal typical iBGP setup, right? So a route reflector relaxes this rule, because of which this is possible. And because of this, what is the first thing we have achieved? We have achieved connectivity, right? Because now this route which this guy was advertising, all the other guys, all the other clients have it, which is great. And second thing is, obviously we have connectivity. In addition to connectivity, we also have reduced number of iBGP sessions, because now the clients need to have just one session with the route reflector. That's it. There is nothing else needed. Cool. The other thing which I also wanted to point out here is on the right hand side, I have put in 3 devices which I'm going to call it as non-clients, right? These are not, I'm just calling it non-clients because they're your typical regular iBGP neighbors, right? Because this is a very possible design in your network. In your network, you might have route reflectors serving few of the peers, right? Which we are going to call them clients. But at the same time, there might be few other devices which are not yet, or which don't want to be clients of this particular route reflector, right? In which case, these 4 routers are going to behave just like your regular iBGP peers, right? So that's why you see there's a full mesh here, correct? You have a full mesh setup. And this is a very possible design as well, right? So I think the main points which I wanted to drive here is, with route reflector, the main thing what we are achieving is we are reducing the iBGP sessions, and at the same time we are achieving connectivity as well. Alright, so now let's get into little more details on this. Let me get rid of my, clear my screen. Okay, so when you talk about route reflector, right, I think what we covered till now, that's the information which most of us engineers kind of have, because that's basically what is covered in most of our certification exams, be it CCNA or CCNP. right? But when you're actually working, right, and if you're really managing route reflector kind of setup, then having more information, especially on the advertisement rules, is very important, right? So let's double click on that. So there are basically three scenarios which I wanted to highlight here. As you see here, there are three scenarios. The first one, let's go with the first one. This is where I have a iBGP peer, right? So this is when I say iBGP, obviously this router and this particular is a different AS, right? That's why it's a iBGP peer. So there's a iBGP neighborship here, and let's assume this iBGP peer is sending an update, right, to our route reflector directly. Then what is the route reflector gonna do, right? We know that route reflector normally reflects the routes, which is great, but in this scenario it is not behaving as a route reflector, correct? Because it is behaving just like a normal iBGP peer. So in this case it is going to send, observe the words which I'm using here. I'm not using the word reflection, I'm using the word send, right? It's going to send those routes to the clients, right? The clients which it might have, and also a non-client, right? This is a non-client which I've shown here. But observe the word I'm using, send, because in this case it is going to behave as a regular BGP router, right? And it is going to send, because in case of iBGP neighborship, we know that what it is going to do. We know that there is always a possibility that there are certain kind of path attributes which might be changed, correct? Right? So you might have certain kind of routing policy, BGP policy based, which is going to change certain path attributes. That's why I'm using the word send here, right? Let's go to the next part, which is the right side. Let me just go to the right. Yeah. So this is the second scenario. This is the most common scenario, right, which we have, where you have the routing update, right, coming in from the client, right? The routing update is coming from the client into the route reflector, and you can see first thing is it's going to reflect that route to other clients, right? That is the whole purpose of route reflector, the major purpose. But then you can also see it is also going to reflect, right, the route to the non-client. So I'm using the word reflect, basically means that it is not going to change anything to the update message, right? The route which is coming in, it's going to as is forward it, right, or reflect it, mirror it, right? That's why I'm using the word reflect. But here you see I'm using the word send towards a iBGP peer, because here in this case it is not going to act as a route reflector in this setup here, right? In this peering, it is going to send, because in case of iBGP we know that there are certain, again, path attributes which might change, like for example next stop might change, right? So in this case it is going to send that update back to or in this case it's going to send it to the iBGP peer, right? So this is again common scenario, right? You might have a route reflector which is doing all its job inside the AS, but it might have certain iBGP peers, it might have certain non-clients, right? This is a very common scenario which you will come across on the field. So you need to understand what the route reflector will do in such scenarios. All right, the last part. Let's come to the right. So okay, the last scenario is where the route reflector is receiving a route from non-client, right? And you can see it is going to reflect it to clients, right? That is one thing, it is going to reflect it. So this is a very interesting scenario, right? Here the route reflector is not getting the route from the client, it is getting it from the non-client. Still it is going to reflect it to the clients, and at the same time it is going to send it to the iBGP peers. I think this we understand. The other thing which I have not depicted here is that what if there is another non-client here, right? In this case what it is going to do here, it is not going to send, right? Because because of the split horizon rule. So it will always, when it receives a route from a non-client, it is always going to reflect it to the clients, it is going to send it to the iBGP peers, but at the same time it is not going to send, reflect, do anything when it comes to other non-clients, right? Because that would kind of break the split horizon rule. Cool. So those are the three rules which I wanted to kind of get you guys acquainted with, because route reflector, we might just, whenever someone asks us, we might just say, hey, it's going to just reflect the routes, but these are all the other possibilities which you might come across in actual network. Okay, there's another point which I also want to drive here. I just remembered before going to the next topic, which is, we talked about this reflection, right? Like for example, in this scenario, we talked about this reflection. Great. It's going to reflect. Like for example, let's take this example itself, right? So you have the route which is coming in from this guy, and we told that the route reflector is going to reflect. But you should also remember that when it is going to reflect, it will do its regular BGP, it will exhibit its regular BGP behavior, that is the best path selection, right? So if it is, let's say for the prefix, right, which this guy is advertising is say 10.0.0.0, right? This particular prefix is getting advertised into the route reflector. So when the route reflector, before reflecting it back, right, it might have received the same route from somewhere else as well, right? There might be another client here who might have also advertised, the same route, right? The same 10. network might have been advertised by this guy as well. So when the route reflector has to reflect it back, right, now it has multiple paths, right? So it is going to do the best path selection using a regular, BGP best path algorithm, and then only the best path is going to be reflected. That's a very important point which I want to drive here, right? It is not going to reflect all the paths, right? For a particular prefix, if there are multiple paths, then it is obviously going to reflect only the best path. That's a very important piece to understand as well. Okay, let's move on to the next section. Okay, so on the very next thing, so once you know what route reflector does, what are the advertisement rules, the very next thing, obviously as a network engineer you're going to think of is how to add redundancy in this design. So now we are actually getting into more on the design stuff, right? So how do you add redundancy? What you see on the left hand side here, this is a very single point of failure kind of a design, right? If this particular route reflector goes down, then all these BGP peers will lose connectivity because their routes are not going to be advertised to other guys, right? Other clients are not going to get those routes, and as a result, the connectivity will be destroyed inside this AS, which is not a good design, right? So that's where you need what? You need like a redundant design, what we see on the right hand side here, right? So here what we have done is we have obviously added one more route reflector, right? This is the AS300. We have added one more route reflector to kind of add redundancy to the network. But as soon as we added redundancy, right, what is happening? Let's actually double click on this. So what is going to happen is, as you know here, these are the clients. These are 4 clients surrounding it and 2 route reflector. It's very important to have full iBGP, peering between the 2 route reflectors. Why? Right? Because we have already spoken about the rules, didn't we? Why do we need full iBGP peering? We need a full mesh setup between the router. In this case, there are just 2 route reflectors, so you just need one iBGP session. But let's say you had 3 route reflectors, then you will need a full iBGP sessions between the 3 route reflectors, because the route reflectors are non-clients, right? So between the non-clients, they are going to act as if they are a regular iBGP peer. So you need a full mesh for all the routes to be propagated between them, right? For all the routes to be advertised between them, right? So that's one very important design piece, that is between route reflectors you need to have full connectivity and full iBGP setup. Okay. Now if you observe this, right, if you trace this, what is going to happen is these are your clients, great, and both the route reflectors are going to get the updates from each client, right? So what is going to happen is, let me see if I can use a different pen here. So there is a update going like this to the route reflector 1, and then there will be a route reflector update going to the route reflector 2 as well, right? And this route reflector will then forward that particular update in this direction as well, right? That is, let's say this is route reflector 1, it is going to send it to route reflector 2, right? So that is going to happen. And what else? The very next thing is, so from a client perspective, what is going to happen? So this guy has done its job. That is, it has sent the updates on to both the guys. Now what is going to happen is that let's probably observe this guy, this route reflector, which is on the right hand side, right? So this route reflector it has received multiple updates for the same prefix, say 10 dot whatever is the prefix, right? It has received multiple updates, so it is going to do that best path algorithm like we spoke earlier, right? And it is going to send or reflect one of the update in this direction to this client, right? But then there is another route reflector, even this guy is going to do the same thing, and that update also is going to be reflected. So at the end of the day, you see this client has received 2 copies, right? 2 copies of the same BGP updates, right? And in a little complicated network with, like, if you have more if you have some BGP policies with attributes and stuff, this can get a little bit messy. That is, it can create routing loops, and we'll actually look at a couple of examples later, right? It can create routing loops. So that's basically what has happened, right? We introduced redundancy in our network, which is great, which is what we like, right? Let me just clear this space. So we introduced redundancy here. We introduced redundancy, but then because we introduced redundancy, there is always a chance of looping coming to play. Okay, so to prevent loops in redundant designs, people came up with clusters, right? So what is a cluster? A cluster is nothing but, even from our previous diagram, right? A cluster is nothing but a route reflector and its associated clients. That is a cluster, right? As simple as that. Even on the right hand side in this diagram as well, assuming that both of these route reflectors have the same cluster ID, then this whole system will be a single cluster. Okay, and I will not double click too much into these two designs right now because we'll talk about this a little later. Let me see if I can zoom in one sec. Okay, so like I said, the only point which I want to drive here is that once people came up with clusters to kind of prevent iBGP loops, right, in redundant designs, they thought, let's go with two types of designs, right? One was where you're using the same cluster ID on both the route reflectors, right? And in this case, the one on the right hand side, you're basically using two different cluster IDs, right? That's why you see there's a yellow and a green color, right? In the left hand side, both the route reflectors are part of the same cluster. You're getting everything what you want, right? Ideally, because you're getting redundancy. You see the clients are connected to two different route reflectors, so even if one of the guy goes down, you have redundancy in place. And that's the same here as well, right? You're getting redundancy. It's just that from a route reflector perspective, they are going to act as if they are in two different clusters here, whereas on the left hand side it is a single cluster. Okay, we'll talk about these two designs a little more in detail. What is the advantage and disadvantage of each of them little later, but yeah, as of now, just remember that to get around the loops which can be caused in redundant designs, people came up with clusters. And how do you identify a cluster? You identify that using a cluster ID. If the same cluster ID is configured on multiple route reflectors, then it becomes a single cluster and it's a single cluster design. Whereas if you have different cluster IDs on the route reflectors, then it becomes there's a name. This actually you call it overlapping clusters, right? The name of this design is actually called overlapping clusters. But ultimately, you're getting, from a client perspective, you're getting the same thing, right? You're getting the same redundancy, because here as well you have redundant route reflectors. You'll have redundant iBGP sessions to both the route reflectors. Here also you're gonna get the same thing on the right hand side as well. Okay, so mainly from loop prevention mechanisms, right? We need to remember two separate IDs or two separate attributes which were introduced. One is the BGP originator ID, and another one is the BGP cluster list, right? These are the two attributes. Let's start with the first one. So BGP originator ID, right? This is an attribute which is created by the route reflector, right? And this is basically created to prevent loops, right? To prevent loops of routing information in a scenario where the route is reflected from the reflector towards the client. Let me explain that with an example, right? So in this case, what do we have? We have a AS100 and this is a different AS600, right? Let me use my pen. So I have a particular prefix here, 100.1.1, and that prefix is getting advertised into this AS using iBGP. Yeah, as of now everything is normal. There is nothing fancy here. Router 1, right, which is like a edge router, right? It is a route reflecting client to these both route reflectors. So there are two route reflectors in this design. This is a client, so it is getting the route and it is going to obviously send it up to, via its iBGP sessions, it is going to send it towards both the route reflectors. For simplicity, let's assume that both the route reflectors have the same cluster ID, which means they belong to the same cluster. That's what we learned right above. Okay, so what will the route reflector do? The route reflector uses this, originator ID. It is going to create this originator ID for that particular route, right? So that's what we can see on the right hand side. Let me just scroll to the right. Just grab this. So let's probably use a different color, right? So this route has come here on RR2. RR2 is going to add the originator ID. What is the originator ID? It is the router ID of the BGP peer which originated the route. In this case it is R1, correct? Because this is the guy who originated that route into my AS, right? So that attribute is added to the route, right? And then that route is obviously reflected because it's a route reflector. It is going to reflect to all its clients. In this case, let's assume, or let's just concentrate on this path. It is going to reflect in this direction. Great. Now sitting here, this RR1 has received it in this direction, and it also has received it, what we talked about here, right, on the left hand side. It has also received the route in this direction as well. So out of these both, it is obviously going to prefer this because we have the local preference value of 200. So ultimately what it is going to do finally is, the update which was received like this, it is going to send it back. It's going to not send it, is going to reflect it, right? Because that's what we talked about, right? Route reflector, at the end of the day, if it gets multiple updates for the same prefix, in this case the same prefix is 100 or 1.1, if it is receiving multiple updates for the same prefix, it will decide the best path and then only reflect the best path. So in this case it is going to reflect the one which came along this direction, and it is going to reflect it back to R1. Now this is where the magic happens. When the route reaches, or the update reaches R1, R1 sees its own router ID in the originator ID, correct? Because that's what we did just now, right? That's the significance of originator ID. Because it sees its own router ID in the originator ID, now it will discard that particular route, right? It will discard the route over here, right? We kind of ended up preventing a routing loop here, right? Because there is no point in reflecting the route which was originated out of R1 back to R1, right? But without originator ID, what would have happened is that we might have created a routing loop here, right? Because the same update would have just gone in circles here. We would have sent it back to R1, there is no really point with doing that, right? So we kind of prevented a loop by using the originator ID. So I just wanted to give an example of how originator ID helps to prevent loops in such cases, especially when the update is reflected back from the route reflector towards the client. That's where the loop is prevented. Okay, the second important tool which you have in your hand, right, to kind of prevent loops is the cluster list. What is a cluster list? It's nothing but a list of cluster IDs. We know what is a cluster ID, correct? It is nothing but an identifier of a particular route reflector and its clients. It's an identifier of the cluster. So cluster list is nothing but a list of cluster IDs. Who is going to create them? Again, the route reflector, right? So let's look at, we talked about the two designs earlier. Let's see how this attribute kind of behaves in these two separate designs. Let me zoom in. Okay, so cluster list, like I said, it is created by the route reflector. So in this case, let's assume we have a client here which is sending an update towards RR1, right? Now RR1, once it receives the update, it is going to reflect it towards its iBGP peer, which is RR2 as well, right? And that update is going to come to RR2, but before sending it to RR2, it is going to append its cluster ID to the cluster list, right? So if I probably use my pen here, so at this point, right, there's my pen. Okay, cool. So at this point, one sec. Yeah, so at this point, we are basically gonna add the cluster ID which we have here. I think it's 1.1.1.10, right? And when that update is sent to RR2, right, the RR2 sees that, okay, the cluster list, right, the cluster list already has 1.1.1.10. So it is going to discard that update. You see, it's going to discard. Why? Because both the route reflectors have the same cluster ID, right? So that's the significance. We just need to understand two things here. One is, when is the cluster list updated, right? That is, who is going to do it? The route reflector is going to do it. Whenever route reflector reflects a particular route, it is going to add its own cluster ID to the list, right? So think of the list as something like this, right? It's a list. As the route is passing through different cluster IDs, right? So in this case, it is 1.1.10, right? Maybe in future, it might pass through a different cluster ID. So in that case, it will add that as well. If there are more clusters. In this case, it is just one cluster. So when the route basically reaches RR2, it will already have this particular 1.1.1.10, right? So R2 will realize that, okay, my cluster ID is already part of the list, so I'm going to discard this particular route. So you see the difference between this and the originator ID, right, which we spoke earlier. In originator ID, the kind of the discard of route happened at the client, but in this case the discard is happening here itself, that is between the route reflector, because you have a full iBGP session between RR1 and RR2 and the discard is happening here. Okay, in the overlapping cluster design which we spoke earlier, here what is going to happen? Here if you see, they are part of two different clusters, right? So when the route reaches RR2, right, in the same example like we talked about earlier, when the route reaches RR2, it is not going to discard. Why? Because its cluster ID is 1.1.2, but it has received an update in which the cluster list only has 1.1.1, correct? So when this guy, is going to reflect this route, downwards like this, it is going to, that particular update will have two cluster IDs in its list. So this will be the cluster list, and it is going to have both 1.1.1.1 and it is also going to have 1.1.1.2, right? Both the cluster IDs will be. Now what is the use of this? I don't know if you have observed this, but in the BGP path algorithm, best path algorithm, there is a, I think, last one step, right, where you can influence the best path using the length of the cluster list. Just like length of AS path, you can use length of cluster list, right? So imagine a scenario where this particular client is getting the same route through some other means, right? And that particular route has a smaller cluster list. In this case, it is 2, but imagine that route had just one cluster ID, right? Then I can prefer that. So generally in the BGP best path algorithm, a shorter cluster list is preferred, right? When you look at the best path algorithm, that's the significance of how you can actually influence the best path using cluster list. Okay, but you saw now there are two designs, and each of these designs you do it slightly differently. Here on the left hand side we saw that we used cluster list, right, to kind of discard the route at RR2 because we were part of the same cluster, whereas in this case the route will not be discarded, right? It is going to get into RR2, and once it gets into RR2, the regular BGP best path is going to be figured out, right? Because RR2, when it has to reflect a route towards the client, it won't reflect all the routes. For a specific prefix, it is going to reflect only one route, right? So it is going to decide which is the best path, and along this direction it is going to only reflect one, right? And ultimately when that route basically reaches the client, it is going to have multiple cluster IDs in its cluster list, right? Which I can then use in my BGP algorithm, in the best path algorithm, to kind of, maybe I can put a policy to kind of filter out certain routes, or I can do whatever I want, right? Once I get this here, if you keep everything default, then the BGP best path algorithm will prefer the route with the smallest cluster list. Now while we are here, we can probably quickly talk about the advantages and disadvantages of these two designs. In the previous case, because RR2 is discarding because it is discarding the route, right? Because of this design, because it is discarding, I would say in this particular design, the routers are saving up on resources, right? Because they don't really have to use their CPU and memory to store those updates, because we are discarding them. We don't really need CPU and resources to process them, store them, and all of that. Whereas on the right hand side, because it is not discarding, it will need little bit of extra CPU and resources to process them and store them. But the disadvantage on the left hand side is that because it is losing this path, it is obviously going to have, it is basically losing the redundant path, right? That's a disadvantage, right? Because technically this path which is coming from here, it might be a better path, or it might have some different BGP path attributes, but we will never know about it because we are directly discarding them on the RR2, because it is in the same cluster. But in this case, what we might end up doing is, because we are not discarding it, we are giving the control, we are giving the decision making to the RR2 to kind of use that redundant path right? And in certain complicated little complex route reflector designs, you also have provision to kind of reflect multiple paths. That's going away from the default behavior, but there are certain ways where you can kind of send multiple paths and stuff, right? So in that case, this becomes very useful, right? Because here we are not discarding that redundant part, rather we are taking it into my RR2, we are processing it, and we can do whatever we want to once we have that route, right? It's not getting discarded. So that's the thing. There's a slight advantages and disadvantages with each of the design. On the left hand side, you will end up saving a little bit of CPU and resources, whereas on the right hand side, you will basically get access to those redundant paths. Okay, so the next thing is I just wanted to put in a quick diagram to show you from my experience, right, working with many service providers over the years. I think the most common design which I have seen is this one, the overlapping clustered ID design, right? This is the one which I have seen in most of the service providers and most of the customers out there, and this is how it looks, right? So here is a simple example. Generally, you look at a service provider, you will have a different point of presence across the globe, or forget the globe, right? Even in a single country, they are going to have different point of presence based on different cities and different regions, different metro cities and stuff like that. So this is a quick example. So I have 3 point of presence for this particular service provider, right, as you see here, right? And you can see we have POP1, POP2 and POP3, 3 point of presence, right? And what are my route reflectors here? I think it's very evident. So these are my route reflectors, right? 1, 2, this is my route reflector, this one, and so we have basically 6 route reflectors, right? And these guys are the clients. Whatever I've highlighted in green is a cluster, whatever highlighted in red is another cluster. So this is what design? This is a overlapping cluster design, right? Because you are getting redundancy. Each of the client has redundancy, but at the same time, they have iBGP sessions to 2 separate route reflectors in two different clusters. That's why it's green and red, right? So this is the design which normally most of the service providers go with, right? And then, like I said, between the route reflectors, you need to have full iBGP sessions. Why? Because these are behaving like your regular iBGP peers. This guy, right? They are behaving like the regular iBGP peers. So you need to have full mesh here. Only then you will have complete connectivity between all your sites and all your POPs, right? So I just wanted to give a quick side note here on what I have seen in my experience, what other people run, right, especially in the service providers. All right, the next very important learning which I want to share with you guys is that whenever you create iBGP sessions in a route reflector design, you need to make sure that it follows the physical topology. You might have seen this statement being mentioned quite a lot, right, in most of the say books out there, but I think it's very important to understand this using an example as well. Okay, so what does this mean? So you see on the left hand side we have an AS, we have a particular prefix 10.1.1, and that's getting advertised into this AS. Great, nothing fancy here. All the dotted lines basically show the iBGP, or basically they show the BGP sessions. So here it is obviously eBGP because it is between AS, right, between A and A1, B and A2, but everywhere else it is iBGP, and we are using T1 and T2 as route reflectors, right? Very important to note here is that A1, right, let's probably write it down here, right? So A1 comma this M2, right, these two are the clients for route reflector T1. Okay, same thing, A2 comma M1 are the route reflectors for T2, right? So what's a very weird thing which you observe here? The weird thing is that you see here the M1, right, it is a route reflecting client to T2. So you see along this line, this dotted lines, but you see it is not following the physical topology, right? That's what I mean by the statement. Logical iBGP session should follow the physical topology. So what I've shown here, this is not the recommended route reflector design. This is not the good way to do it because it can create loops, right? Because you see M1 is forming iBGP with T2, right? But actually M1 is physically connected with T1. So technically this should have been the case. It should have formed, or it should have acted as a client to T1, not to T2. But here we are, right? So what is this going to create? What issue will this create? Let's have a look at that. Okay. So just okay, so we know the problem. So what we understood that we have intentionally created the problem on the right hand side to explain this scenario where M1 and M2, they are not forming iBGP sessions along the physical topology. They are just it's actually doing the quite opposite. Okay, so what's going to happen? This particular prefix, it is going to come into my network. Great, it's going to come in to A1 and A2. Now A1 and A2, A1 is obviously going to send that update up, and A2 is also going to send it to T1, T2. On T1, what is going to happen? Let's assume that both T1 and T2 are part of the same cluster, right? So they are part of the same cluster. So same cluster ID, which means that we saw the design earlier, that is the update which this guy gets, which is going to send it down here. This guy is going to discard it because they have the same cluster ID. Same thing in the other direction as well. The update which goes like this guy is going to discard it, correct? Which means that these updates are of no use for me. So what's going to happen? T1 ultimately has just this update which came along this, and it is going to send it along this direction. Same thing T2, it is going to receive the update from A2 and is going to send it along this direction, right? And M1 and M2, M1 sitting here will think that it can reach 10.1 using what is the next hop? A2. Right, let's actually clear this. So M1 will think that it can reach this guy using A2. At the same time, let's use a different color. M2 will think that it can reach this guy using A1 because it has received the update only from T1. Right, that's what's going to happen. Now let's try to trace this. So let's trace. When I say trace, I mean let's get on to this M1 box, and if I do a ping to 10.1.1, what's going to happen? Right, I'm on M1, I'm trying to ping 10.1.1.1. So when I do that, first what's going to happen? M1 is going to look at its BGP, it's going to look at this routing table. From the routing table, it will realize that to reach 10.1.1, the next stop is nothing but A2. Right, it is A2. But to reach A2, it will have some IGP running here, right? Let's assume it is EIGRP. There will be some EIGRP generally, or some kind of IGP which is running inside, AS, right? So it is going to do a recursive lookup to the next hop, which is A2, and obviously the best path to reach A2 will obviously be along M2, right? Say like this, it's going to come here. So the packet will come to A2, but on will come to M2. On M2 again, it is going to do a routing lookup because that's how a router works, right? As soon as it gets a packet destined to 10.1.1, it is again going to do a routing lookup. And it is going to find that its next stop to reach is A1, right? And using EIGRP, it figures that to reach A1, it has to go like this. So you see what has happened here? The packets will continuously loop here. M1 will send the packet to M2, M2 will send it to M1, and the packets will continuously loop. The reason why this happened is because we did not follow the physical topology. The iBGP sessions which were created here did not follow the physical topology. To solve this problem, what we should do, instead of having these iBGP sessions, we should actually have iBGP like this, right? That is M1 and A1 should form route reflecting clients to T1, and M2 and A2 should form iBGP with the T2. So with that in place, what would happen is that when the update comes in like this and the update comes in like this, right? It is again going to be discarded along this path because it has the same cluster ID, but at least the update which comes to T1, it is going to send it to M1. The update which comes to T2, it is going to send it to M2. So on M2, right, the next stop to reach this particular route will be A1, not A2, right? So this will be the next stop, right? And because of EIGRP, it will forward the packets along this direction. And as a result, there won't be any routing loop. M2 will do the same thing and it will reach the destination using this path, right? You see, just by changing the iBGP, we were able to get that working. So that's very important. That's why it's very important to always make sure that your iBGP sessions always follow the physical topology. Always have that point, if you forget anything else from this lecture, make sure that you carry that point. Your iBGP session should always follow the physical topology. Alright, the last topic which I want to cover in this design discussion is the hierarchical route reflectors, right? let's actually go one diagram above, right? So I talked about this ISP design here. In this ISP design, what really happens is, the problem with this design is that as your ISP grows, right, as the network becomes huge, at one point of time, the iBGP sessions here between the route reflex, it becomes quite a large, right? So you will end up with too many iBGP sessions between the route reflectors. I mean, we introduced route reflectors to reduce the iBGP sessions, but you know, in such a scenario, right, you will end up having if the network becomes quite big, then you will end up having quite a lot of iBGP sessions between your route reflectors. So I would say hierarchical route reflector design is a good fit for you if you are in such a scenario. The idea is pretty simple, right? In hierarchical route reflector design, a router which is a route reflector for one of the cluster can become route reflecting client for another cluster, right? So here you can see, let's look at this diagram. Let's try to understand this. How many routers do we have here? Don't worry about the labels and the clusters and everything. For a minute, let's observe total number of routers. We have 4 plus 2, 6, 6 plus 3, 9, 11 plus 3, 14. So 14 routers, right? If I did not have route reflectors at all, then I would have needed to have, use my pen, I would have needed to have 14 routers and full iBGP mesh between the 14, correct? Full iBGP mesh, which means that it is going to be 14 into I think it's going to be 13 into 7, right? That'll be total number. Let's not worry about the total sessions, but I'm just telling we'll need to have full mesh between 14 routers if you did not have route reflectors at all. Now let's go and add the first level of route reflectors, which is, say cluster 10 and cluster 20, right? Why we are dividing into two clusters to begin with, obviously that's another discussion, but obviously you want to you want to break your network into clusters because you don't want to just use two route reflectors for the whole of your network, right? Because then those two route reflectors will have too much of work, right? They will need to have too much of CPU and RAM because all the updates are sent to them and all of that. So ideally you would need to have multiple clusters. That's why you need multiple clusters. So we are going with two clusters to begin with, cluster 10, cluster 20. And with this design, what did we do? The full mesh sessions got reduced to what? Because you have route reflector here, now the number of full mesh sessions will be 1, 2, 3, 4, 5, 6, 7, 8. So from 14 we went to 8, right? Just by adding these two clusters. Forget about cluster 100. We just added two clusters. So if you added two clusters, then now the full mesh sessions are going to be between 1, 2, 3, 4, 5, 6, 7, 8, between those 8. So you need still full mesh, but between the 8 routers. Now let's go and add the next level of, we'll add one more cluster, which is cluster 100, right? And when you're adding cluster 100, you are adding these two route reflectors and these are the clients, correct? So but because of that, now the full mesh sessions go from 8 to what? 1, 2, 3, 4, 5. So we reduced from 8 to 5. Now the full mesh sessions are reduced from 8 to 5, which is pretty cool. But this is where it gets even more interesting. Some brilliant person thought, what if I can further reduce from 5? How about I make these routers, which are actually already route reflectors. So these routers are already route reflectors for cluster 10 and 20. How about I make them route reflecting client, right? How about I make them, they will continue with their role. They are already route reflecting route reflectors, right, for these two clusters. But in addition to that, how about I make them clients to another cluster, which is cluster 100 here, right? So these will still remain to be route reflectors, but these are going to act as a clients for this route reflector. So that's where the hierarchical comes into play, right? Now because of that reason, the only full mesh I want is only between these both guys, right? So I reduced from 5 to what? 2. Now the total iBGP full mesh which is needed is only between two pairs. We started with 14, we went to 8 because we did all these clusters. We added one more cluster and we reduced it to 5. But then from 5 we are able to reduce it to 2 because of this hierarchical route reflector design, because what we made is we made the route reflectors as clients to different route reflectors, right? That's pretty cool. Let's quickly trace what is going to happen when an update is received. Okay, so when an update is received, let's probably use the pen again. So let's say we have an update coming in from this client, right, for a particular prefix. That update is obviously going to be sent to the route reflector, right? That route reflector is then a client to a different route reflector. So that update will be sent upstream as well, right? It's going to be sent or reflected. So here it was reflected, but then from here it is going to be advertised again. And this route reflector has its own clients, right? So it is going to be reflected here. So you see the update flows through the whole network. But there is also a possibility, because you are basically sending this here. There is also a possibility that same update might come back into your own cluster, right? It goes from cluster 10, it goes to cluster 100, but there is a possibility it might come back to your own cluster. But what is going to help here? Cluster ID is going to help, right? We learned about cluster ID, correct? Cluster list and cluster ID. So when this route reflector sees an update come back, and it is seeing its own cluster, because every time a route reflector is reflecting a route, it is going to append the cluster ID. So it is going to add this cluster ID, the ID of cluster 10, and it is going to send it. So when it comes back, this route reflector will be able to see its own cluster ID in the cluster list, and it is probably going to discard that particular update, right? So that's how you can prevent loops using the cluster list in a hierarchical route reflector design. Okay, cool. Alright guys, so that's mainly everything which I wanted to cover. Honestly, just to recap, if you see from the top, we started with the why we need the route reflector, right? We talked about a little bit of the nomenclature of route reflector design. We spoke about the various advertisement rules. Remember, all the three ones, they are very important, because the most common one we see across is the middle one, but then you also need to know what will happen when a route reflector receives a route from, say, iBGP or from a non-client, right? Then we talked about how to add redundancy to our design, which was pretty simple, just adding maybe one or multiple route reflectors. But then as soon as you add redundancy, there is, you will end up with loops, right? There's a possibility of loops. So to kind of get around that, people came up with the clusters. Now when you go to clusters, again you have two types of designs. Either it is single cluster or something like this, overlapping cluster, where you have ultimately the clients are getting redundancy, but this is just changing the perspective of the route reflector, right? Here you have just one single set of route reflectors. Here you have like two separate systems, because it is two separate clusters. Now loop, when you talk about loop prevention, we have mainly two attributes which are introduced. One is the originator ID, and this kind of prevents the loops in a way that at the clients mainly, right, at the route reflecting clients, because as the updates are reflected back to the clients are going to use the originator ID to discard the routes when it sees its own originator ID in its own router ID in the originator ID, right? And cluster list again is another way to prevent loops. This is mainly when it's mainly used when you have multiple layers of route reflectors, like a hierarchical design. So if there is an update which is sent from my cluster to another cluster, right, and then in future if it is planning to come back, if that update is sent back to my own cluster, I can discard it, right? So we talked about again how it is going to behave in a single cluster and overlapping cluster design, the use of cluster list. Then we talked a little bit about the large ISP design, right? How generally what people use out there, which is overlapping cluster design, right? Something like this. And we talked also about how not following the physical topology while creating iBGP sessions can land you in trouble. It can create loops. So always make sure your iBGP sessions are in line with the physical topology. The next thing is finally we also learned about hierarchical route reflecting design, right? This will basically help you to kind of when your network grows, if you don't employ this design, then you will end up with a lot of full mesh iBGP sessions between your route reflectors. But creating hierarchies of this sort, don't also go and create too many hierarchies. Maybe keep it to one or two layers, because if you create too many hierarchies, then it will further complicate your network and manageability becomes difficult. So create 1-2 layers of hierarchy of this sort, and we saw that how it can drastically help you to reduce the full mesh sessions needed between the route reflectors, right? Thanks a lot for watching. Have a good one. Thanks guys. Bye.